Alright, welcome back to Turing Complete. In the last one we talked about basic logic gates. We finished all the bigger ORs, the bigger ANDs, XNOR, XOR, and of course all the stuff before. Now we're getting into the more fancy stuff like memory, and I'm going to leave these are the memory ones, right? Bit and red. No, these aren't. As you can see, there's a little bit of side dependency, but I want to do all of these first and then go into these because some of these rely on these. So this is the arithmetic side of it. This is the math. Probably won't get through all of these right now, maybe just these 7, but we'll see how long it takes. So start with binary eraser. Oh, that was my favorite pastime, converting decimals into binary under time pressure. Oh, well, for those of you who don't know, the way binary works is like in base 10, right? This position would be worth 1, right? Like this is, so 10 times 0 is 1. So whatever number is here is just that number. This position would be the tens place, right? So a 2 there would mean 20, a 3 would mean 30, so on. And that's the number just get. Binary, same way, but powers of 2 instead of 10. So 1, 2, 4, 8, 16, 32, 64, 128. That's how computers count. So toggle the bits, so they add up to the decimal number in question. Must beat level 3 to pass. All right. There's 1, easy. 2, easy. 3, 2 plus 1. 13, 8 plus 4 plus 1. 6, 4 plus 2. 11, 8 plus 2 plus 1. 12, 8 plus 4. 1, already did that. 14, 8 plus 4 plus 2. 22, 16 plus 8, oh, plus 4 plus 2. 21, 16 plus 4 plus 1. 2, 2, 4. 19, 16 plus 3, which is 2 plus 1. 31 is all the ones. Since that's a multiple, that's easy. Or one less than a multiple, I meant. 32 plus 5, which is 4 plus 1. 62 is 32 plus 16 plus 8 plus 2 plus 4. Yep. 32 is even. I almost missed that other one. 4 plus 2 plus 1. 38, 32 plus 4 plus 2. 42, 32 plus 8 plus 2. 38 is 32 plus 6. 14 is 8 plus 4 plus 2. 18 is 16 plus 2. 47 is 32 plus 8. There we go. 71, 64 plus 8. Oh. 121 is... Nope. That was close. I can't read them aloud fast enough. Oh, perfect. Oh, damn it. I didn't mean to click submit twice there. I reached level 5. I don't know how long this goes. I kind of want to try again, but I'm not. Hopefully you notice there's exactly one way to write each number. The value of each divot is always double the previous. Yeah. Got it. Onwards. Okay, so double trouble. Because we're so technologically advanced, we have machines fold our socks. Unfortunately, the circuit that detects sock pairs broke the machine. Alright. This level has 4 inputs. Output on when 2 or more of them are on. Tip, don't overthink. Alright. So if at least 2 of them are on, it counts. Well, it says don't overthink. Well, if I just do a bunch of, see, it's 2 to the, how many options are there? There's 4, right? So there's 4, there's 2, 4, 6, 8, no, 2, 4, 8, 16, sorry. Different different events that can happen, right? So if we just make a bunch of AND gates, and this is by no means the most efficient way to do this, by the way. I'm going to make it look nice just for fun. Oops. Right, if we move this up here, by think of this like each one of these, right, will affect half. No, wait, this will only try with 3 others. Hold on, I confused myself again. This goes into these 3. This goes into here. And then 1 here. And then 1 here. That's 3. This will go into 1 here. Oh, make it look nice. This will go into this one here. And then 1 with this one. And then this last one, which we know will, of course, be with this guy, who will do 1 with the first. When I said I was going to make this look fancy, that was before I overthought things. I also completely miscounted. I know I could just do this how it's set up, but is this right? So I'm pretty sure if any of these, let's see. Yeah, see now if any 2, I didn't really explain what I was doing. Basically, this is all the combinations of 2. Right, because this one, oh, because it's a combinatorics, that's why the math is wrong. It's just 3 times 2 is how you find the end, right? Why is it not 4 by 2? Should be 4 by 3. There should be 12, shouldn't there? Well, we'll see. And then of course we have the 3. We don't have the big AND gate. Where's the big AND gate? Hold on. It saved your progress. Did I not do the bigger AND gate? Where's my big, I know. Where's my big AND gate? I want my big AND gate. Oh, just do like we did before of this, ANDed with this, ANDed with, okay, well that looks bad if I do it that way. ANDed with this. And for now, it doesn't actually matter if we make these space efficient. It's purely a matter of aesthetic, but it will matter once we start doing actual CPU implementation. Okay, so I'm stupid. This should be OR gate. Because if it's any of these Archer, and I have the triple OR. Gentlemen, I may not have a brain, but I have an idea. That's off-center. That's gonna drive me insane. It's okay. This is okay. This is what I deserve for being stupid. See, now it's on, because if any of these not. See, it's easy to mix yourself up, because Boolean algebra is weird. Alright, now, odd number of signals. Using a maximum of 3 components, output on only when an odd number of inputs are on. Well, has a hint if you get stuck. Oh, I remember this level. I don't remember how I did it. if an odd number is on. So that's just an XOR gate, right? If I XOR these, or if I XOR these, it's only, does 0 count? 0 should be off, but 1 should be on. 2 should be off. 3 should be on. So yeah, just 3 XOR gates, right? Oh, is this correct? Am I a genius? I am a genius. I'm gonna run that through because that might not be. I mean, you can add comments to wires. That's a thing. How long has that been in the game? Anyways, so basically, an XOR gate is really just checking if it will output 1 if odd. Because that's, I mean, that's what, right, 1 or 1 input. So if we know that the upper 2 is giving an odd number, right, and the bottom 2 is giving an odd number, if they're both giving an odd number, well, that makes an even number. Odd plus an odd equals an even. But if only one of them is, you know the answer is odd. Thus, you layer XOR gates. All right, let's do the counting signals. The output component of this level is a binary counter where the first 3 pins, where do I get this wire comment? Cool. The output component of this level is a binary counter where the first 3 pins correspond to 1, 2, and 4. 1, 2, and 4. No, that's the output. 1, 2, and 4. Yeah. So you see that's a binary 3-bit number. So since it's 3-bit, it can represent 2 to the third minus 1 as the maximum, right? So 2 to the third is 8, minus 1 is 7, because if it's all 3 are on, that's 1 plus 2 plus 4, which is, of course, 7. Use the binary counter to display the number of signals. Check this hint if you get Sonic. The solution of this level is not very neat and requires more components. Oh, good, good. Okay, so the way I'm going to break this up is piecewise first, and then I might try to go back and make a neater one. So we just figured out how to check if it is even, right? Or, excuse me, if it's odd, right? We just use 3 XOR gates. I'm going to make a bus of, for y'all who don't know, a bus is just a bunch of wires. That's all a bus is, right? This is a 4-wire bus right here. And so, and then this makes it really easy and neat to organize wires. I could color code them if I want. I'm not going to here because I don't think that's necessary yet. So this, right, will be on if it's odd, right? 1, not 2, but 3, and so on. Well, we know that since this bit equals 1, right? Well, any odd number will have a 1 component because every number after doubling, right? Every number after 1 is even because you can always divide by 2 because you just multiplied by 2. So this first bit will be 1 only if it's odd. And we know, right? See if we counts 1, but then if we do 3, right? Well, now it should say 3. So this should also be on. So this next one needs to check. I guess we could just check if it's divisible by 2. No, that won't work. Because 4 is divisible by 2, and that should only be the last one on. Oh, but we did have that gate that would turn on if only 2 of them. Didn't we do that? Just took a bunch of AND gates. Right? If we had... how many inputs did we have at that? We had 4, so, and we ended up with 6, right? We had this, and this, and then this, and this, and then this, and this, and then you start over with this one, but this one, and then the second, the last, and then the only thing that's left is this and this. Now, if any of these are, I know it said it's not going to be neat, but I'm gonna try to make it neat anyways. Is this enough room? Yeah, it is. Oh, I said this. I guess this isn't that neat, but not the neatest thing I've ever made, but you know. Right, so this we just made. This we made 2 levels ago. Or rather, essentially, right? Make that up. I like 90-degree angles sometimes. So now, counts to 3. And then it just goes back to 2. When it should be 4. Okay, so this isn't quite right. So this, let me move this out, is going to be this should only output if this is true. I know this is gross, but I'll need another signal. So I want this to always be, can I rotate? How do I rotate? There's a rotate button. I know it. How do I swear there's a way to rotate. Oh, rotate, space. Oh, of course it's space. Play campaign. Oh, it saves my progress. I knew it did, but. So now, right, we'll do this. Oh, I can't do that. Now, see, this is on. But, get rid of these. See, now, if this 4 is going to be on, right, so if this is high, this needs to turn off, which means whatever is carrying this signal needs to also turn off this input, right? Because as soon as it goes to 2, as soon as it goes to 4, the 2 needs to be off. So now we have to determine if all 4 are on. Which we can do with this same setup, but ands, right? Right? I can actually do this with less components, I am now realizing, but, you know, hindsight's 20/20, and we all know how well that went. That is gross. That is perhaps the grossest, but works flawlessly. Tip, there's no shame in using pen and paper. That is fair. Binary. Yeah, base 2, base 10. See, since it's in the second place, it's 2 to the first. Because it's the 0 plate, 2 to the 0, 2 to the first, 2 to the third, so on. Yeah. Cool. I'm going to do the double one. And I'm gonna leave it off there. For this is getting into, this has all just been the foundations of arithmetic. So I think doubling is the next piece of arithmetic that we need to go over. Yeah. The input and output of this level are using bytes instead of bits. One of the 2 new components you were given takes a byte and splits it into bits. The other does the opposite. Using those components, figure out how to double the input number up to 127. Yeah. So, for those who don't know, a byte right, is just 8 bits, right? So a byte can have a max value of, see, it's 8 wires, right? That's what this, say, 5, 6, 7, 8. This 8-wire bus, that's what these are, right? And if you pull it out of a component that uses bytes, it'll automatically, it's a bus of 8 wires. Oopsies. Cool. Just so you know. So, outputting a byte, and we need to double it. So, if we think about it, we're in base 2. And in base 10, everyone knows that the easiest number to multiply by is 10, because when you multiply by 10, you just shift everything to the left and add a 0. So, it works the exact same way in base 2, except since it's base 2, it's 2. So, I need to shift this up. So this 1 would become 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, and so on and so forth. 128 gets dropped because it can't go that high, right? This should technically be asserted low. Like there should be a 0 going into here. I know it's implied, but I would like to have it there just for good practice. But see, it runs, it does all the runs all the tests. Cool, yeah. There's an entry on bytes. Game asks you to build an 8-bit computer. Practically, this would normally require the player to put down 8 parallel wire lines in many places. To alleviate tedious busy work, you're given the notion of a byte, which is just a virtual bundle of 8 bits. State of either a byte input slash output or wire line is represented by a number instead of the red or green color. Yes, because, right, when you have, how do you represent that these ones are on and these are off? Well, with a number, right? Because 117 can only mean the 1 bit is on, 2 bit is off, 4 is on, 8 is off, 16 is on, 32 is on, 64 is on, 128 is off. That's what 117 can only mean, is the reason they do that. Okay, so that's all for now. We got through the very foundations of arithmetic, right? This and of bit. We even got into bytes, right? Bigger data amounts. So I think that's good for now. So check in next time.